We saw that symmetric matrices are orthogonally diagonalizable and can be decomposed into the product of an orthogonal matrix P by a diagonal matrix by the transpose of P, where D is a diagonal matrix with the eigenvalues of A on the main diagonal, and P is a matrix of orthonormal eigenvectors of A. Now there are other decompositions that exist to simplify matrices that can't be orthogonally diagonalized. So for example, if A is any square matrix with real entries, and if it has real eigenvalues, then there's an orthogonal matrix P such that its transpose multiplied by A by P is an upper triangular matrix. And this upper triangular matrix has the eigenvalues on the diagonal and some values above the diagonal and all zeros below the diagonal. So denoting this matrix product as S, then A is equal to PS P transpose, and this is called the Schur decomposition of A. And for a matrix A with real entries, there's another decomposition called the upper Hessenberg decomposition. So similar to the Schur decomposition, we have an orthogonal matrix P multiplied by the matrix A multiplied by P, but in this case we end up with a matrix H. So this square matrix has a main diagonal, and below the main diagonal we have a subdiagonal, and all entries below this first subdiagonal are 0. And all entries above can be non-zero. So in this case A is equal to P H P transpose is the upper Hessenberg decomposition of A. So as we can see, these types of decompositions have restrictions. And if we look for a decomposition of the following form, where P is not an orthogonal matrix, so in this case J is the Jordan canonical form, which can be a diagonal or block diagonal matrix, then if we take this approach, then we lose the length preserving property of orthogonal matrices. So for example, taking the norm of an orthogonal matrix by a vector xe, which is an estimate to some solution vector x, then the norm of the product of an orthogonal matrix by the estimate minus the same orthogonal matrix by the exact vector is the same as the norm of xe minus x, being the length of the error vector. Because an orthogonal operator P does not stretch x, and therefore does not magnify any round-off errors, which is important in the accuracy of computer algorithms. So instead of looking for this decomposition, where P may not be orthogonal, we're going to look for another decomposition, being the singular value decomposition, where A is decomposed into a product of an orthogonal matrix by a diagonal matrix by the transpose of another orthogonal matrix. And this method can be applied to orthogonally diagonalized non-square matrices. A singular value decomposition can be applied to a general matrix that is not square. And a key symmetric matrix that's involved in this method is the transpose of a matrix A with P rows by Q columns multiplied by A. So this matrix is symmetric because if we take the transpose, we can see that we end up with A transpose by the transpose of A transpose, which gives us back A transpose A. So given our P by Q matrix A, the fundamental matrix spaces of these two matrices are practically the same. So firstly, the null space of A is the same as the null space of A transpose A. So recall the solution to the homogeneous linear system is the null space of A, and the solution space of the following homogeneous linear system is the null space of A transpose A. And as an exercise, have a go at verifying this for these given two matrices. And because the row space of A is the orthogonal complement of the null space, then that's equal to the row space of A transpose A, which is the orthogonal complement of the null space of A transpose A. And from this relationship, it's also the orthogonal complement of the null space of A. And the column space of A transpose is equal to the column space of A transpose A. So note that because A transpose A is symmetric, the column space is equal to the row space. And if we transpose a matrix A, the column space of the transpose is equal to the row space of A. And the rank of A is equal to the rank of A transpose A. Because note that the row space of A and the column space of A have the same dimension, which is the rank of A. And similarly, the row space of A transpose A has the same dimension as its column space. So therefore, given the row spaces are the same, the ranks are the same. And the eigenvalues of A transpose A are 0 or positive. So A transpose A is at least positive semi-definite. Given a matrix A with P rows and Q columns, then if the eigenvalues of A transpose A are denoted lambda 1 to lambda q, then the singular values of A are denoted sigma 1 being equal to root lambda 1, sigma 2 is equal to root lambda 2, up to sigma q being equal to root lambda q. So for example, if we decompose A into an orthogonal matrix U by a diagonal matrix sigma by the transpose of an orthogonal matrix V, then transposing A will give V transpose transposed by U sigma transposed. So that will be equal to V by the transpose of sigma by U transpose. And now if we multiply A transpose by A, we get V sigma transpose by U transpose by U by sigma by V transpose. And given that U is an orthogonal matrix, this product will give the identity matrix. So we end up with V by sigma transpose by sigma by V transpose. And therefore this matrix is a diagonal matrix that consists of the eigenvalues of A transpose A. And therefore V is the matrix of orthonormal eigenvectors that orthogonally diagonalizes this symmetric matrix. So if each eigenvalue of A transpose A is denoted as lambda I, then given this product of sigma transpose by sigma, which will have the eigenvalues on a diagonal, we set the eigenvalues equal to sigma I squared. And therefore, taking the square root of both sides, we get the singular values of the matrix A, being the square root of the eigenvalues of the symmetric matrix A transpose A. And generally we'll order the eigenvalues of A transpose A from largest to smallest, and therefore we order the singular values of A from largest to smallest. So let's take a look at this example and get rid of this. So if we want to find the singular values of A, we take the transpose of A and multiply it by A to get this matrix. And then we solve the characteristic equation to get the eigenvalues. So we have 5 minus lambda squared minus 4 by 4 is equal to 0. And therefore lambda squared minus 10 lambda plus 25 minus 16 is plus 9 is equal to 0. So therefore we can factorize this polynomial as lambda minus 9 by lambda minus 1. And therefore the eigenvalues of A transpose A are lambda 1 is equal to 9 and lambda 2 is equal to 1. So therefore the singular values of A are sigma 1 is equal to root lambda 1, which is 3, and sigma 2 is equal to root lambda 2, which is 1. As we briefly mentioned, given a P by Q matrix A, we can express A as the product of an orthogonal matrix U with the diagonal matrix sigma and the transpose of another orthogonal matrix V. So the diagonal entries of sigma are the singular values of A, with all other entries 0. And recall when we took the transpose of A and multiplied it by A, we obtained V by U epsilon transpose. So that gave epsilon transpose U transpose. And multiplied by A, we have U by sigma by V transpose. And given that U is orthogonal, U transpose U is the identity matrix. So we obtain the following expression. And similarly, we can multiply A by its transpose. So here we have U by sigma by V transpose by the transpose of V transpose and by the transpose of U by sigma, which gives sigma transpose by U transpose. And again V is orthogonal, so V transpose V is the identity matrix. So we get this expression. So as we can see, we multiplied A transpose by A to get this matrix, and we obtained the eigenvalues, and therefore the singular values of A are obtained as follows. So sigma 1 is the square root of lambda 1, which is 3, and sigma 2 is the square root of lambda 2, which is 1. And here for each eigenspace corresponding to those eigenvalues, we obtain the eigenvectors V. And similarly, we computed A by A transpose and obtained the eigenvalues, which I'll leave for you as an exercise. So we can see these eigenvalues are the same as those for A transpose A. And we obtain the eigenvectors U for each eigenspace corresponding to each eigenvalue. And now we're ready to decompose A into this product. So let's copy this decomposition of matrix A down here to make a bit more space. So our matrix U has the normalized eigenvectors in each column. So the norm of U1 is equal to the square root of 1 squared plus 1 squared plus 4 squared, which is root 18. And therefore, we have 4 on root 18, 1 on root 18, and 1 on root 18 in the first column. And the norm of U2 is root 2. So in the second column we have 0, minus 1 on root 2, and 1 on root 2. And finally, the norm of U3 is the square root of 1/4 plus 1 plus 1, which will give you 3 on 2, or 1.5, and therefore minus a half on 3 on 2 gives minus a third, and 1 on 3 on 2 is 2/3, and we have 2/3 again. So this is our matrix U, which is a 3 by 3. And now let's construct the matrix V, which we expect to be a 2 by 2. So the first eigenvector goes in the first column, and we normalize it. And the second eigenvector gets normalized and goes in the second column. And then we transpose this matrix V to get V transpose. So flipping this negative sign. So therefore V transpose is a 2 by 2 matrix. So our matrix sigma is expected to be a 3 by 2. And we put the singular values of A on the diagonal and zeros otherwise. So that's our matrix sigma being a 3 by 2 matrix. So you can verify that this matrix product is valid. So the number of columns of U are equal to the number of rows of sigma, and a number of columns of sigma are equal to the number of rows of V transpose. So this is our singular matrix decomposition of A. And I encourage you to actually evaluate this product to verify that you get back the original matrix. Now another thing to note is that if you multiply both sides of this equation by V, we get AV is U sigma, and as we saw, V has each eigenvector in its columns, and sigma had the singular values of A on the diagonal and zeros otherwise. And similarly U had the orthonormal U vectors in each column, being the orthonormal eigenvectors of A transpose. So therefore, if we compute AV1 for example, that's equal to U1 by sigma 1 or sigma 1 by U1. And then we have AV2 is sigma 2 by U2. So in general, we have AVI is equal to sigma I by UI up to I equals R, where R is the rank of A. So therefore U is an orthonormal basis for the column space of A. And as we saw, V orthogonally diagonalizes A transpose A, and U orthogonally diagonalizes A transpose, and sigma contains the singular values of A on the diagonal.